What if I told you that every grain of sand on Earth, every mountain, every continent, including the very atoms in your body, began as invisible specks of dust floating in the vast emptiness of space? It's a mind-bending reality that challenges everything we think we know about planetary formation. Consider this. A typical grain of cosmic dust is 1,000 times smaller than the dust mote floating in a sunbeam in your living room. Yet, somehow, these impossibly tiny particles manage to clump together across millions of years to create objects as massive as Jupiter, a planet so large it could contain over 1,300 Earths. The journey from microscopic dust to massive worlds represents one of the universe's most extraordinary transformations. But here's the mystery that has puzzled scientists for decades. By all known physics, these dust particles should simply bounce off each other when they collide. They should drift apart, get pulled into their host stars, or be blown away by stellar winds. So, how do they overcome these seemingly impossible odds to build the planetary systems we see throughout the galaxy? Today, we're embarking on a cosmic construction project spanning billions of years from the first dust grains born in dying stars to the rocky worlds that might harbor life. We'll explore cutting-edge discoveries that are rewriting our understanding of how planets form and discover why this process might be far more common and happen much faster than we ever imagined. What do you think is the most remarkable part of planetary formation? Share your thoughts in the comments. Does the idea that we're all made of ancient stardust change how you see our place in the universe? To understand how dust builds planets, we need to grasp the cosmic recycling system that makes it all possible. Picture the universe as a vast construction site where the building materials, the elements heavier than hydrogen and helium, are manufactured inside the cores of massive stars. When these stellar giants reach the end of their lives, they don't simply fade away quietly. Instead, they explode as supernovae, hurling their newly forged elements across space at incredible velocities. This cosmic debris containing carbon, silicon, iron, and dozens of other elements begins to cool and condense into tiny solid particles, no bigger than smoke particles. This is cosmic dust, the universe's raw construction material. Think of space as a vast, three-dimensional ocean where currents of gas and magnetic fields carry these dust particles across light years. Unlike the static dust on your bookshelf, cosmic dust is constantly in motion, orbiting stars, colliding with other particles, and gradually accumulating in the spinning disks of material that surround young stars. These protoplanetary disks are where the magic happens. Imagine a cosmic pizza made of gas and dust, with a newborn star at the center providing heat and energy. The disk rotates, with particles closer to the star moving faster than those on the outer edges, just like how Mercury orbits the Sun faster than Neptune. In this environment, something remarkable begins to occur. The disk isn't uniform. It has temperature gradients, density variations, and complex magnetic fields. Near the star, it's hot enough to vaporize most materials, but farther out, in what astronomers call the snow line, water can freeze into ice. This creates different zones where different types of materials can survive and begin the slow process of accumulation. The transformation from individual dust grains to planets involves several distinct phases, each presenting unique challenges. Scientists have identified what they call the meter-size barrier, a seemingly insurmountable obstacle where growing dust clumps become so large that they should be destroyed by collisions or spiral into their host star. For decades, this barrier represented one of planetary science's greatest puzzles. The journey from dust to planet begins with forces so subtle they were barely understood until recent decades. When two microscopic dust grains, each smaller than a bacterium, drift close to each other in space, they're influenced by forces that seem almost magical, van der Waals forces and electromagnetic attractions that can cause them to stick together despite their tiny masses. Professor Anders Johansson from Lund University, who has spent years studying this process, explains, planet formation takes place when these dust particles collide, and they grow to larger and larger sizes. This growth takes us from micrometers all the way up to 10,000 kilometers or so. During the first million years of a planetary system's life, the host star is in what astronomers call the T-Tauri phase, a period of violent stellar winds and intense radiation. Paradoxically, this seemingly hostile environment actually helps planetary formation. The stellar winds create turbulence in the protoplanetary disk, stirring up dust and increasing collision rates. Recent observations using the Atacama Large Millimeter Array have revealed something extraordinary happening in the Taurus star-forming region, just 450 light-years from Earth. Scientists tracked millimeter-sized dust clumps being swept by stellar winds from the chaotic inner regions of forming planetary systems to the calmer outer edges. There, away from the gravitational pull and destructive collisions near the star, these fortunate particles can grow larger before migrating back inward. This discovery helps solve the meter-size barrier problem. Dr. Philip Hopkins from Caltech describes the challenge. If you throw two pebbles together, they don't stick. They just bounce off each other. For sizes between a millimeter and hundreds of kilometers, the grains don't stick. This is one of the biggest problems in modeling planet formation. The solution lies in what Hopkins calls the Hopkins-Squire instability, a process where gas flows around dust particles create complex interactions. When many dust grains exist in close proximity, the combined gas flows channel particles together into clumps, overcoming the tendency to bounce apart. Temperature gradients also play a crucial role through a process called thermophoresis. Large cold dust aggregates create temperature differences in the surrounding gas, causing smaller particles to migrate toward them down the temperature gradient. This effectively creates an attractive force that can increase aggregation rates by up to 6 orders of magnitude. As particles grow beyond centimeter size, gravity begins to play an increasingly important role. What starts as electromagnetic and van der Waals forces gradually gives way to gravitational attraction. Particles become planetesimals, mountain-sized objects that can survive collisions and continue growing through gravitational accretion. The final phase occurs when these planetesimals reach roughly 1,000 kilometers in diameter. At this point, gravity becomes strong enough to compress the irregular rocky debris into spherical shapes, the birth of true planets. For gas giants like Jupiter and Saturn, this solid core then becomes massive enough to capture vast atmospheres from the surrounding disk. Remarkably, new research suggests this entire process happens much faster than previously thought. Dr. Anja Anderson from the Niels Bohr Institute notes, there seems to be enough cosmic dust to potentially create Earth-like planets within a few 100 million years following the Big Bang, suggesting planets and possibly life could have emerged when the universe was still very young. The process of planetary formation from cosmic dust raises profound questions about the prevalence of planets throughout the universe and the likelihood of life emerging elsewhere. Recent discoveries have forced scientists to reconsider several fundamental assumptions about how and when planets form. One major debate centers on the timing of dust production in the early universe. Traditional models suggested that several generations of stars needed to live and die before sufficient heavy elements existed to form rocky planets. However, observations from the Very Large Telescope and Webb Space Telescope indicate that dust formation occurred much earlier than expected. This has revolutionary implications for astrobiology. If Earth-like planets could form within the first billion years after the Big Bang, life might have had a 12 billion-year head start in some parts of the universe. As Dr. Anderson points out, this revelation suggests that the possibility of life in the universe, including intelligent life, might have had a substantial head start around 12 billion years ago. Another area of intense research focuses on the role of electric charges in dust aggregation. Recent experiments under microgravity conditions, simulating interplanetary space, show that dust particles develop strong electrical charges that significantly affect their collision behavior. This electrical component of planetary formation was largely overlooked in earlier models, but appears crucial for understanding how particles overcome the bouncing barrier. Scientists also debate whether the planetary formation process we observe in our solar system is typical or unusual. The discovery of thousands of exoplanets has revealed planetary architectures very different from our own systems, with hot Jupiters orbiting closer to their stars than Mercury, or super-Earths, with no analog in our solar system. These observations suggest that the dust-to-planet process can produce dramatically different outcomes depending on local conditions. The amount of dust available, the temperature structure of the protoplanetary disk, the intensity of stellar winds, and even the presence of nearby massive planets can all influence how and where planets form. Some researchers propose that planetary migration, where formed planets spiral inward or outward from their initial positions, plays a crucial role in determining final planetary configurations. This would mean that the dusty birthplaces of planets might bear little resemblance to their final locations. Current missions and future telescope projects are poised to answer many of these questions. The James Webb Space Telescope can observe protoplanetary disks in unprecedented detail, while upcoming missions like the Roman Space Telescope will study how dust and gas move through our galaxy on vast scales. These investigations aren't merely academic. They're reshaping our understanding of cosmic evolution and our place within it. Every discovery about planetary formation helps us better understand not just how Earth formed, but whether the conditions that led to our existence are common or extraordinarily rare in the cosmic landscape. The transformation of microscopic dust grains into massive planets represents one of the universe's most remarkable construction projects. From invisible specks smaller than bacteria to worlds capable of supporting complex life, this process demonstrates the power of gradual accumulation across cosmic timescales. What we've discovered challenges many assumptions about planetary formation. The process happens faster than expected, can occur much earlier in cosmic history, and involves complex physics that we're only beginning to understand. Electric charges, temperature gradients, gas dynamics, and gravitational instabilities all work together in ways that make planet formation not just possible, but perhaps inevitable around many stars. This research has profound implications for our search for life beyond Earth. If planets can form quickly and early in cosmic history, if the building blocks are more abundant than we thought, then the universe might be teeming with worlds, some possibly harboring life forms that evolved billions of years before Earth even existed. Perhaps most remarkably, this cosmic construction process continues today. Right now, in star-forming regions across the galaxy, dust grains are beginning their billion-year journey toward becoming planets. Some of those distant worlds might one day host their own curious beings, wondering how their own atoms came to be arranged into thinking matter. But here's the question that keeps astronomers awake at night. If planetary formation is so common and can happen so quickly, why don't we see more obvious signs of advanced civilizations in our galaxy? Is there something special about the dust-to-planet-to-life sequence on Earth? Or are we missing something fundamental about how often this process leads to intelligence? As we continue to study protoplanetary disks and discover new exoplanets, we're not just learning about cosmic construction. Every grain of dust tells a story spanning billions of years, connecting us to the stars that forged our elements and the worlds yet to be born. Subscribe to GeoCurious and join us as we continue exploring the universe's greatest construction projects. What aspect of planetary formation amazes you most? Are we alone in the universe, or are countless other worlds forming from cosmic dust right now? Share your thoughts below. Your curiosity drives our next cosmic adventure.